Bismillahirrahmanirrahim. Assalamu alaikum, dear students. We are now starting the first lecture for week number 6 for our course of communication systems. In our last week's discussion, we concluded discussion on amplitude modulation and its variants. We have discussed both time domain and frequency domain representation of AM signals, as well as the different circuits that we use to generate AM signal and its variants. Further, we have also discussed some strategies how we can demodulate the AM signals to get the information signal out of that modulated signal. So for today's discussion, we'll be starting the discussion on angle modulation or exponential modulation. If you recall, in the discussion of AM modulation, the AM modulation is basically classified as the linear modulation, as the modulated signal is actually representative of the information. So it resembles what the modulated signal resembles the message signal. However, for angle modulation, the modulated wave does not resemble the message signal. Rather, the modulated waveform has a constant envelope. So with this sense, this exponential modulation or angle modulation is generally represented as non-linear modulation. There are two major categories of this angle modulation: phase modulation and the frequency modulation. So for this week's discussion, we'll be focusing on these two modulation techniques, that is phase and frequency modulation. So before we start the detailed discussion on each of these modulation techniques, let me quickly highlight some of the differences between the linear modulation and exponential modulation methods, so that we can focus on these things when we have detailed discussion during the analysis. So we know that the linear modulation, these are the variants of AM modulation that we use and classify them as linear modulation: AM, DSB, SSB and VSB. For phase modulation, we have two major techniques, which is for angle modulation we have two major techniques: phase modulation and frequency modulation. In case of linear modulation, the envelope of message signal is dependent, envelope of the modulated signal is dependent on the message signal. Actually, it follows the message signal. However, in exponential and phase modulation, the envelope is generally constant, so it remains constant. We have also discussed that spectrum of the modulated signal is actually same as what we observe for unmodulated signal. It's only the same spectrum appears at a different frequency, so it only provides a frequency translation with no significant change in the spectrum. However, we will observe that in exponential modulation, the spectrum would be rather complicated, so it will not be exactly representing the message signal spectrum. So there will be a complicated relationship between the spectrum of the unmodulated and modulated signal. The bandwidth that we have discussed is actually given as 2W. For AM and DSB, we know that the bandwidth is 2W. For SSB and VSB, the bandwidth is close to the message bandwidth, that is W. So the maximum bandwidth that we can get in AM or linear modulation is actually twice of the message bandwidth. However, for the case of exponential modulation, we can get the bandwidth which can be greater than this 2W value. Rather, it can be further increased by appropriately setting the modulation parameters. So we can have even larger bandwidth, for this case exponential bandwidth. Another important thing is signal to noise ratio. For modulated signal, the signal to noise ratio is actually less than or equal to the baseband signal to noise ratio. This small b here, it represents a baseband signal to noise ratio. So modulation actually does not improve the signal to noise ratio. Rather, if we need to improve it, we need to increase the transmission power. So from modulation there is no effect on the SNR. However, for exponential modulation, the signal to noise ratio can be greater than the baseband signal to noise ratio. So modulation actually provides some improvement in the signal to noise ratio as well, even without any increase in the transmission power. So there is an improvement in signal to noise ratio, but at the cost of increased bandwidth. We have also discussed that there will be an increase in bandwidth. So if we increase the bandwidth of the modulated signal, we also get an increment in the signal to noise ratio. So generally what we need to do, we need to create a compromise between the bandwidth and SNR, so that we can get an optimum value of the signal to noise ratio and a reasonable value of the bandwidth for the better performance of the signal. So in this sense, in most cases, the exponential modulation performs better than the linear modulation. So this was an overview and comparison between the linear modulation and exponential modulation. So let us now move on to the detailed description related to this exponential modulation techniques, that is phase modulation and the frequency modulation. As we have previously discussed in AM case, that we have to look at both aspects, that is the time domain representation as well as the frequency domain representation. Similarly, for this exponential modulation case, we'll be discussing both time domain representation of the modulation as well as the frequency domain representation. So let me start with providing some basic information related to the frequency modulation. So as we know that the frequency modulation means we change the frequency of the sinusoidal carrier in accordance with the information signal. So the information is actually represented by varying frequency of the sinusoidal carrier. So this modulation frequency, so this technique is named as frequency modulation. So in other words, when we are using frequency modulation, the carrier amplitude remains constant. So we do not make any change in the carrier modulation. Rather, the carrier frequency is changed by the modulating signal. So the carrier frequency is actually proportional to the amplitude of the modulating signal. So we can say that as the amplitude of the modulating signal increases, the carrier frequency would also increase, and similarly if the amplitude decreases, the carrier frequency would also decrease. And of course, if there is no modulating signal, so the carrier will be transmitted at its normal frequency, which is sometimes called resting frequency. So the resting frequency is the frequency where the carrier is not modulated. So it represents actually the frequency of the carrier. As we know that a frequency would be changed when we use frequency modulation, so there is a maximum amount of change that can be created by the modulation. So that maximum amount of change is generally named as the frequency deviation. So frequency deviation represent what is the maximum change in the carrier frequency that is produced by the modulating signal. Another term which is used in conjunction with frequency modulation is frequency deviation rate. So frequency deviation rate is actually represent how many times in a second the carrier frequency deviates above or below the carrier frequency, the center frequency. So because it will go above the frequency and below the frequency, the number of changes, it is represented by frequency deviation rate, and this frequency deviation rate is actually dependent on the frequency of the modulating signal. So if modulating signal has higher frequency, this frequency deviation rate would be very high. One of the variant of this frequency modulation which is used in the digital transmission. For digital, as we know that there are specific number of symbols, like for binary there are only 2 symbols. So we can use this frequency modulation for digital as well, but in that case this frequency modulation is named as frequency shift keying, FSK. FSK is actually same thing as the frequency modulation but applied to a digital system. Okay, let us now get a basic discussion on the phase modulation. So in phase modulation, of course, the carrier carrier phase is actually changed in accordance with the modulated signal. So the frequency remains the same. We do not typically we do not change the frequency, rather we change the carrier. But we should realize that frequency and phase both are in the angle. So whenever we change either frequency or phase, the overall angle would change. So phase change also affects the frequency, that we will be discussing in subsequent slides, inshallah. So the phase modulation is achieved whenever the phase shift is proportional to the amplitude of the modulated signal. So phase modulator produces some phase shift. So the greater the amplitude of the modulating signal, we will be having a greater phase shift, and smaller value of the amplitude of modulating signal would be represented as a smaller phase shift, and even the negative amplitude would be represented as a negative phase shift. So basically this is representative of the phase modulation, that we have to observe the phase in order to retrieve the information of the information contained in the phase modulated message. So the maximum amount of the phase shift occurs at the peak amplitudes of the modulated signal. So peak amplitude would give the maximum phase change, and other amplitude would give a relatively smaller phase change. Similar to the frequency modulation, we can apply this phase modulation in the case of digital data as well, for binary data. But in that case, the phase modulation is named as phase shift keying. So phase shift keying is actually the digital version of the phase modulation. Okay, with this we have a basic idea related to the phase modulation and the frequency modulation. I try to explain some basic terms related to the phase and frequency modulation. Let us now try to develop a mathematical representation of both PM and the FM signals. So we start our discussion with the time domain representation, and at later stage we will be discussing the frequency domain description of both PM and FM signals. So let us consider a continuous wave signal with a constant amplitude or constant envelope. So this amplitude AC is taken as constant because for both PM and FM the amplitude would remain same, but the overall phase would be different. So this signal would be represented as this value, AC cos omega ct plus phi. So this xct represents the modulated signal where you have performed the modulation at this angle, and this modulation is represented by this changing phase in the signal. So in that case the total instantaneous angle would be represented by this value theta ct is omega ct plus phi t, where phi t is actually representative of that message information. We can also represent xct in exponential form. We know that cosine is actually the real function, real part of this e raised to power j theta. So as we know that from Euler's identity, e raised to power j theta is actually cos theta plus sin theta. So cos theta plus j sin theta. So you can see that from here this cos theta is actually real part of this e raised to power j theta, so we can represent it like this. And you can see that as the angle is represented in exponential form, that's why we generally use the term exponential modulation or angle modulation, because it's actually representative of this angle or this exponential function here. Okay, so we this would be a mathematical form of the modulated signal. So what is the theta t here? So let us start with the phase modulation first. So phase modulation, as I previously mentioned, that instantaneous phase phi t is linearly dependent on the modulating signal. So this phi t, this phase, is actually proportional to the xt, the message signal. So in that case, if we try to represent it mathematically, so it will be represented somewhat like this. Phi t should be equal to some constant number which is represented as phi delta xt. This phi delta is actually representing the maximum amount of phase change that will be achieved during the modulation. And of course, in order to avoid ambiguity, this phi delta should be kept smaller than 180 degree, because greater than, if phi delta is greater than 180 degree, we will not be able to demodulate the signal, because there will be an ambiguity in the phase because of the changes more than 360 degree. So in that case, the maximum phase change that will occur in the modulated signal would be starting from minus phi delta up to plus phi delta. So whatever phase change we would have, that will lie in this band. So if phi delta is equal to 180 degrees, so the maximum change that you will be getting will be from minus 180 degree to plus 180 degree. And that's why we need to keep this phi delta smaller than 180 degrees, so that we can detect the phase without any ambiguity. So this phi delta, as I mentioned, is the maximum phase shift, and it should have the value of 180 degree. And from the sense of this proportionality, this phi delta is representing the proportionality constant in this expression, representing the relationship between the message signal and the phase of the modulated signal. This phi delta is named as phase deviation or phase modulation index. Therefore, the overall modulated signal would be represented like this: xct is equal to ac cos omega ct with some constant frequency plus phi delta xt. So this is the mathematical form of the phase modulated signal. You can see that the phase is dependent on this xt, which is message signal. If I ask you what is the instantaneous frequency for this signal, so we have this phase modulated signal here. So if I ask you to represent the instantaneous frequency, so actually this part, this is the overall angle. Instantaneous frequency is actually represented by this relationship. This dot here represents the first derivative with respect to time. So if we differentiate the angle with respect to time and divide it by 2 pi, so we would be getting the instantaneous frequency of the signal. And you can quickly see from here, if you differentiate with respect to time and divide it by 2 pi, you would get the instantaneous value to be equal to fc plus this delta t, phi t derivative divided by 2 pi. So phi t is actually d phi t by dt, but we know that phi t is also dependent on the message signal, as we have defined this instantaneous phase as in direct proportionality with the message signal. So phi t is phi delta into xt. So therefore we can write instantaneous frequency to be equal to ft equal to fc plus phi delta 2 pi x dot t, where x dot t is actually first derivative of xt. You can see that instantaneous frequency is also not constant in this case, as the frequency would also be changing, but that change is related to the derivative of the message signal, whereas the phase change is actually direct proportionality with the message signal. So the phase modulation, actually we would see the changes in phase as well as the frequency, but we give it name phase modulation as the phase is in proportionality with the message signal, whereas frequency is not in proportionality, rather it has a relationship with the derivative of the signal. So this is the mathematical representation of the phase modulated signal. Let us now move on to the frequency modulated signal. So how can we represent the frequency modulation for a signal? So what would be the instantaneous frequency? Actually, instantaneous frequency should be directly proportional or linearly proportional to the message signal. So we represent the instantaneous frequency to be equal to message signal multiplied by some constant, which is f delta. But we should know that there is a base carrier frequency, or it's a resting frequency as well, so which is represented by this constant frequency term fc. So the instantaneous frequency is dependent on two parameters. One is fc and second is this variation with because of the variation in the message signal. So you can easily see that as the message signal would change, the ft would change. If xt is positive, so if message signal has a positive amplitude, the instantaneous frequency would have a relatively higher frequency than carrier frequency, and if xt is negative, the message modulated signal would have frequency which would be smaller than the carrier frequency. Therefore, the maximum deviation that we can get in this case, so frequencies that will be present in this signal would have the minimum value, which is fc minus f delta, and the maximum value that we can get for the frequency would be fc plus f delta. And you can see that this f delta is actually representing the maximum amount of the deviation that can be obtained by using this frequency modulation. So this f delta is named as frequency deviation. So frequency deviation represents the maximum change that will be achieved when you are using frequency modulation. One important thing you should note that this f delta should be much smaller than this carrier frequency. Carrier frequency should be large enough, and the deviation cannot be greater than the carrier frequency in any case. So you can easily see that this frequency change here is actually in direct proportionality with the message signal xt. If I ask you regarding the phase, So we can also calculate the phase as well. Eventually, as I mentioned previously, in case of phase modulation, the phase will also be dependent on the message signal. So what is the relationship? We have to refer to this relationship here. Ft is equal to Fc plus phi t derivative divided by 2 pi. We can use this relationship to calculate the phase. Ft is known here. You can substitute Ft here and simplify this expression for phi t. If you solve it for phi t, so you would see that the phi t would have a relationship that involves integration of this message signal x lambda. So this phi t is given by this expression, where this phi t naught is the starting phase or initial phase which is observed at some time t naught. Typically in our signal analysis, we take this initial phase to be equal to 0. So typically it becomes 0. In that case, we can simply ignore this term and the overall phase would be represented by this phi t. So we can write phi t to be equal to this value 2 pi f delta and integral of x lambda. You can, from this relationship, you can see that this instantaneous phase is also dependent on the message signal, but that relationship is not linear. Rather, we need to integrate the message signal in order to obtain the instantaneous phase of the modulated signal. So if I ask you to represent the mathematical form of a FM modulated waveform, so this waveform, the general form is given here as we discussed previously. It has a constant amplitude, it has some frequency and phase. But for FM case, now we know that this phi t is actually related to the message signal by a relationship of integration, which is shown here. So by substituting this value, we can represent the FM modulated signal like this: xct would be equal to AC cos omega ct plus 2 pi f delta integral of x lambda d lambda. So this is the mathematical representation of the frequency modulated signal. You can compare it with the phase modulated signal, which was represented here. For phase modulated signal, this phi t can be represented by phi delta xt, whereas in FM signal this phase can be represented as 2 pi f delta integral of xt. So for FM signal, you need to integrate the message signal to get the frequency modulation. This is a summary of the relationships that we have discussed so far for frequency and phase modulation. Actually, there are two parameters that we are discussing. One is the instantaneous phase of the modulated signal, and second is the instantaneous frequency. And the third parameter, which is the amplitude, should be treated as constant for both PM and FM signals. So for PM signal, the instantaneous phase is directly proportional to the message signal. So instantaneous phase is represented as phi delta xt, whereas the instantaneous frequency is dependent on the derivative of the message signal. So instantaneous frequency of the PM signal is fc plus phi delta upon 2 pi x dot t. So x dot t is the first derivative of the message signal. Similarly, for FM signal, the instantaneous frequency is directly proportional to the message signal. You can see that the instantaneous frequency is dependent on f delta xt. So as we change the message signal, so the instantaneous frequency will change linearly. Whereas the phase has a rather different relationship. The instantaneous phase of FM signal is dependent on the integration of this message signal. So you can get the instantaneous phase by integrating the message signal and multiplying by 2f delta. Another important thing that we should notice that we cannot distinguish FM and PM signals by observing the waveform, because there would be no change in the envelope. The envelope is actually a constant for both cases, for frequency modulation as well as the phase modulation. So the entire information is actually located in the zero crossings alone. So how the signal change, and whenever it crosses the zero axis, zero amplitude axis, so that zero crossings actually represent the information. So in order to retrieve information for both PM and FM, we actually need to observe the zero crossing points in order to exactly retrieve the information that is contained in that frequency modulation or phase modulation. So another important thing is the power for FM and PM signal. We have previously discussed that power is dependent on the carrier amplitude. For carrier amplitude, the power is generally given as AC square by 2, and we know that for both PM and FM signals, though both have this constant amplitude, so that means the power in both cases, they are dependent on the amplitude only. So the power does not depends on the deviation. So if we increase the frequency deviation or the phase deviation, we should notice that there will be no increase in the power. So power is independent of the deviation. But if you recall, in amplitude modulation, the overall power was dependent on mu as well, the amplitude modulation index. But for this case, the power is independent of that deviation. We have discussed that there are lot many similarities between PM and FM signals, but it is worth mentioning that FM modulation performs better in noisy environment. The reason is because the F delta can be set to an arbitrary value. We can have relatively large value of F delta, whereas we cannot have much large value of phi delta. Phi delta can have the maximum value which should be equal to or less than 180 degrees. So phi delta cannot be larger than this value, but for frequency deviation, F delta can be as large as needed. So this provides this flexibility in choosing the value of delta, provides designer to set the value in order to have a better performance in the noisy environment. As I also previously mentioned that it is possible in FM case, it is possible to have a better signal to noise ratio without increasing the signal power, and that better signal to noise ratio comes from the fact that the instantaneous frequency is actually dependent on this xt and F delta. So if we increase the value of F delta, so overall this factor gets increased, and eventually we get a better signal to noise ratio. But the drawback in that case is that we need to have a larger bandwidth. So it requires bandwidth which is much larger than the previous case, so that so there is a compromise between choosing appropriate bandwidth and the signal to noise ratio. So we can improve signal to noise ratio at the cost of increased bandwidth. So there would be a need of compromising what is the appropriate value of signal to noise ratio and what is the bandwidth that should be implemented in a specific application. So concluding the discussion related to FM and PM signal, I am quickly representing a comparison by representing the time domain waveform for each of the signals. So we have AM modulated signal, FM modulated signal and PM modulated signal represented here. So there are two representation. One is based on this modulating signal is a triangular wave. In second case, the modulating signal is taken as the sinusoidal wave. So you can see that the amplitude modulation, we have this constant amplitude and which gets increased in accordance with the message signal, and then it suddenly decreases and comes to the message signal value. Similarly, you can see at FM signal, the frequency is changing with respect to the amplitude of the modulating signal. You can see that starting from here to here, at this point, because the amplitude is relatively high, you see a relatively high frequency or fast oscillation here. Similarly, the phase is represented by change in phase. You can see that the phase is increasing as the amplitude modulation is changing. You can see that the phase is moving forward gradually in accordance with the message signal, and at this point where you see a sharp change in the modulating signal amplitude, you can see a sharp change here in the phase of the PM signal here. Similar observation can be seen from this sinusoidal modulating signal. You can see that for amplitude modulation, the carrier amplitude is changing in accordance with the message signal, whereas for frequency modulation, the larger amplitude, they are related to a relatively fast variation in the signal, that is a relatively high frequency, whereas this negative amplitude represents the slow frequency, slow variation, that is the low frequency in the modulated signal. Similarly, for phase, you can see that the high amplitudes are corresponding to the relatively higher phase, whereas the low amplitude, they are represented by a relatively smaller value of the phase angle. So these are the waveforms, time domain waveforms related to AM, FM and PM signals. So for this lecture, we'll conclude our discussion at this stage. So far we have talked about the time domain representation of FM and PM signal, and we have also discussed the relationship between the instantaneous phase and the instantaneous frequency for both PM and FM with the modulating signal. In our next lecture, inshallah, we'll be discussing some frequency domain representation of this FM and PM signal. So we stop here. Thank you all.